Good evening. This is Group 25. Our project was reinforced contrastive attention-based capsule networks for retinopathy diagnosis. So, as you can see, these are the names of my group mates. They'll also introduce themselves. My name is Among Tracy. So, the contents of our presentation, just briefly, we have the introduction, we have related work, problem statement, research questions and objectives, research contributions, methodology or system architecture, dataset description results, the conclusions, anticipated limitations and counteraction plan, and the acknowledgements. So basically, to give you a brief background and introduction, our project was basing on the disease, diabetic retinopathy. So we know diabetic retinopathy is a disease that comes about, okay, the eyes get damaged due to prolonged high sugar levels within the blood system. So of course, this is diabetes. Yes. So what happens is that the red blood vessels get damaged. So it can lead to either partial or permanent blindness. So there are two types of diabetic retinopathy. We have the non-proliferative diabetic retinopathy, sorry. So in this one, it's just the early stages of the disease. Here, the blood vessels are damaged, yes, but they're not yet at the point of growing abnormally. Then we have the proliferative diabetic retinopathy. Now, this is the advanced stage of the disease. Here, the blood vessels start to grow abnormally and they are fragile and weak, so they can easily start leaking blood, which eventually leads to permanent vision loss. So here, as you can see, recognized as one of the leading causes. One important thing that you should note is about 30 to 40% of people in the world suffer from diabetic retinopathy, which deems it a global issue, a global problem. So in this project, we intended to use CNNs, which are convolutional neural networks, and then capsule networks as well as transfer learning. Then in the early now, one of the important things is our project is basically for early stage detection so that we prevent permanent vision loss, which could happen in the long run in case testing is not done. So now here we just have a few images from our data set. As you can see from the no DR signs, we do have a very normal eye and the retina. There is no hemorrhaging of the blood vessels. Everything looks normal. But if we go and maybe look at the very severe here, you can see that some of the blood vessels have actually started to hemorrhage or to bleed. Now what happens is they burst. Remember, they grow now when they're abnormal and fragile, so it's easy for them to hemorrhage. Then we have the severe NPDR. Now this is a severe stage of the early part of the disease. Remember, we have the NPDR and PDR. NPDR is the early stage where the blood vessels are still growing normally, but then for the PDR, here they've now started growing abnormally. So now, some of the related works, or yes, the related works or the literature review. Some of the related works that we see here is that we have the CNN-based DR detection. So we have examples of the models. So basically, what that model was meant to do, it works by learning some of the features through convolutional layers. So it learns the features from the retinal images. Then now here the layers automatically learn the relevant features. For example, we have the presence of blood vessel abnormalities or the lesions, which are all some of the subtle features of DR. When we go to the next related work, which is ensemble learning and attention mechanisms, we have some of the examples there. So basically what goes on here is that it combines multiple models to improve overall performance. Now, these attention mechanisms help to focus on the most important parts of the image or the most important features, such as the blood vessels, which are useful in identifying the subtle signs of DR. Then we'll move to the capsule networks for the DR classification. For capsule networks, basically it's for it what goes on there is the models establishing relationships between the features, and then it involves learning how the different parts of the retina relate to each other and how they're affected by the diabetic retinopathy. Then for the final one, contrastive learning for medical images. What we know about contrastive learning, basically it's grouping into similar and dissimilar pairs. So how is this useful in the diagnosis? It helps in training the model to distinguish between images of a healthy retina and then those with DR. Then how our work differs from this, as you can see, we implemented capsule networks and contrastive learning, which enables better classification. We have reinforcement learning, based attention. Here, basically, we're focusing on critical retinal features. Once you see attention based, then we have the optimized computational efficiency. Now, majority of these models are computationally demanding. They could either require a lot of memory and all those things. Then we also have handles class imbalance. So we are able to implement a more robust and reliable DR detection. So I'll invite my next colleague to take us through the next part of our presentation.
Good evening. My name is Jude, and I'll continue from where one of my colleagues has ended. So, I'll be describing the problem statements in this slide. The domain application problem. This is the problem that we are trying to solve by our work. And one of the problems are the detection of diabetic retinopathy. Early detection is very crucial to prevent vision impairments, since if it reaches the if it reaches the latest stages, if you know the latest stage, if it reaches the PDR, the proliferative diabetic retinopathy stage, it becomes very hard to treat, and the chances of treating it even become lower. So the traditional diagnosis relies on manual retinal image examination, which is, of course, time consuming, it is inconsistent, and requires specialists. And it is usually not accessible in remote areas. Then the computational problem, these are the problems that we shall face as we are trying to tackle the domain application problem. One of them is the high resources. Since we are building capsule networks, it requires heavy computing space and memory, which is a computational problem. Then the class imbalance. Some classes, like the mild class, had a data imbalance, although we applied some different techniques to handle that, but the problem was class imbalancing. Then misclassification. Sometimes the model struggles to classify two closely related stages of DR. So it's also one of the problems. Then image sensitivity. Some images have noise, which greatly affects the prediction of the model. So the next slide, the resource, I mean the research objectives. We have some research questions here, as you can see, like how accurate is our model. These were the questions we took into account while we're building our model. The key features in the retinal images of the RA CapsNet. Then, can this model effectively differentiate between different stages? We took into account all these questions, and we made sure when we're developing the model, we're doing something that actually does what we claim it will do. Then, the research contributions, we deployed the the model using CNNs and hybrid models. This is the methodology, the flow diagram. Let me go through it quickly. So at the top, we have the image that is given to the model by the user. Then the model will pre-process it. The pre-processing and milling can be in terms of resizing it, then normalizing it, or even augmenting it. Then after that, it moves on to the convolutionary layer, the CNN. This CNN extracts the important features of the image, like the hemorrhages and the most important features. And then we move on to the primary capsules. The primary capsules converts these important features from the CNN into capsule networks. Since our model is a capsule, is using capsule networks for diabetic retinopathy. Then we move on to the dynamic routing. The dynamic routing, this is a method CNNs use to determine the most important features that will greatly affect the performance of our model. From there, we move on to the contrastive attention model. Here, here in the contrastive attention model, we have spatial relationships, and we also have something that we call feature discrimination. Feature discrimination is important in avoiding false positives, since it is very crucial not to have false positives in this field. Then we move on to the reinforced attention weighting. The reinforced attention weighting is here the model assigns weights. The model assigns weights to the feature and makes sure and it makes sure it it maximizes the weights or the reward. Then after that, the output, since we have 5 classes, the output will be one of these classes that are seen down here. So that is the flow diagram of our model. So the data set description, we have 7 classes. The NODR, we have something like, we have 187 images. Then the mild non-proliferative diabetic retinopathy, we had 4 images there. Although I told you we use some techniques to avoid data imbalancing. Then we have the moderate NDPR, the severe, the very severe, and the PDR, together with the advanced PDR. So my friend will come and continue from there.
Good evening. My name is Tom Elvis Rodney. I'm going to take you through the dataset description and exploratory data analysis. Actually, my friend talked about the data imbalance. So with the data imbalance, this could make our models a bit biased. So we had to come up with a solution to this problem. So we carried out adversarial learning on majorly the mild dataset to try to create synthetic images to make up for the 4. As you could see, it was largely imbalanced. So this is how our PCA visualization was after carrying out the adversarial learning. As you can see, the clusters of the mild is a bit significant compared to the PCA visualization we had before the adversarial learning, and you can also see the other clusters of the different classes of DR. Then if you go to the expected results, we train different models on our new data set, trying to, after catering for the data imbalance, we tried different methods, but this one, the one you're actually seeing, where we carried out adversarial learning on the mild data set, actually produced better results. So we have different, one of the hyperparameters we have was training rate, then we have the accuracy, how our models perform, we have precision, recall, F1 score, and then the specificity. But all these all this we in order to get our best model, we have to rely on recall and precision, where precision, this measures the proportion of the correctly predicted positive instances out of the instances predicted as positive. Then recall measures the proportion of the correctly predicted positive instances out of all the actual positive instances. Then the F1 score is just a ratio of precision and recall. So basically, we wanted a model that I recall, I precision. Precision is how confident is our model in predicting these. As you can see, some models really had very low accuracy, like the CNNs, and then deep caps and reinforced capsule networks also had the what? Their accuracy wasn't that high, the precision and the recall. And then when you come down, you see things like the vision transformers really performed very well. The VIT, the DEIT version of the vision transformer really performed well. Then we have the swine transformer. The swing transformer also performed really well. It, it had an high accuracy, the precision was high, and then the recall was also high. Let's move on to our EDAs. As you can see, let's move on to our confusion matrix for the different models. As you can see, the deep caps really didn't. They performed well. They were able to predict in the node DRR science, and basically our project, we are supposed to be able to predict the diseases in the early stages. Like we need a model that's supposed to be able to perform very well in the first 3 or 4 stages. But as you can see, also the other stages were important. But if you see the NASNet with contrastive learning didn't perform so well towards the end, the last 3 stages, all these models had a problem there, but they were able to predict in the first 2 stages well. Then the other models, we have the reinforced capsule network, the VGG16 and the 19. The VGG16 really performed very well. It was able to predict the models in their specific, though it also misclassified a good number of a good number of the classes. We don't want something of this kind. Then the VGG19 really disappointed us. I think it was because of maybe its architecture. Then when you come to lastly, we have things, and now our title, our research was basically on the reinforced capsule network, contrastive attention-based capsule networks. It performed well compared to other models, but it also in node DRR science misclassified a lot of the classes. Then the mild, it performed well. Then the moderate also performed, but also misclassified the number. Then you can see our winner is obviously the vision transformer. The swing vision transformer, it was able to classify the models with few misclassifications. My colleague will take you through from here.
Hello, I'm going to take you through the conclusions and limitations plus the future works. So in the conclusions, we have improved accuracy, handling class imbalance, automation, and efficiency. So these outcomes are what we expect from the models that we have built and also from generally the project. Then conditions, we have high computational demand, we have sensitive to image variability, then need for diverse data sets. Then the limitations are the problems we are facing as we have been going on with our project. Then the next steps in the future works, like what we are hoping to add on to our project is improved data augmentation. And with that, we can use GANs and realistic data augmentation images. Then contrastive learning optimization, then the use of hybrid models. These we can combine vision transformers and CapsNets for a better pattern detection. Then we have Edge AI and mobile development and multimodal learning. So this will integrate OCT scans. We can use fundus images, and this can improve our accuracy during our diagnosis. Yes. So these are the recommendations we have for our future works. Then the acknowledgements. Thank you very much.